there's this contradiction between the physics, which seems fundamentally reversible, and so much of our life that seems irreversible.
Though it flies in the face of everyday experience, the laws of physics actually say bizarre things like these are possible. But how could this be? Well, the answer is not as far-fetched as you might think. Here's why. We all know what will happen if I drop this glass of wine. Now, the idea that this mess could somehow reverse itself and form back into a solid glass filled with wine seems absurd. But according to the laws of physics, this can happen. All I need to do is reverse the velocities of everything. Every piece of glass, every drop of wine, every molecule and atom in the liquid, glass, table, and air. Just reverse all their velocities. And voila! So, if the laws of physics don't care about whether glasses shatter or unshatter, why don't we ever see them unshatter? How can we square the laws of physics with our everyday experience? Something must be missing in our understanding, but what? What's responsible for the arrow of time? Like many good mysteries, this one leads us to a graveyard in our search for clues. In Vienna, near the
Where is he? Oh, you heard that.
I'm resting places of Beethoven, Brahms, Schubert, and Strauss is 19th century Austrian physicist Ludwig Boltzmann's tombstone. Etched on top is an elegant equation, S equals K log W. It's the mathematical formulation of a powerful concept known as entropy. Entropy is a measure of something that we're all familiar with, disorder or randomness, and it's an important idea because there's a tendency of everything in the universe to move from order to disorder. Here's a way to get a feel for the idea. Take my book, all 569 pages of it. It's very ordered, with the first page followed by the second, followed by the third, and so on. But now, let's tear the pages out and let entropy go to work. As you can see, the pages become very disordered, and the reason is simple. There is only one way for them to land in order, but a huge number of ways for them to land out of order. And so it's much more likely that they'll land in a total mess. And this is what we experience in our daily lives. Things move from order to disorder. In this case, from a neat ordered book to pages that are randomly scattered. Everywhere we look, we see examples of entropy or disorder increasing with the passage of time. An egg breaks and splatters. Ice cubes lose their orderly shape as they melt into water. Billowing smoke becomes increasingly disordered.
Ordered states become disordered states. And that appears to be perhaps the direction of an arrow of time.
We see sort of degrees of messiness, a measure of disorder, tend to increase in one direction of time.
And so that, for Boltzmann, begins to create an arc of time.
So maybe this is the answer. Maybe the arrow of time comes from the tendency of nature to evolve toward ever greater disorder.
We're going to stop there. The arrow of time is a very catchy phrase, very useful in a cocktail party. Okay, so remember, we said that for the second law, according to the second law of thermodynamics, delta S of the universe is what? Delta S of the system plus the delta S of the surroundings. Greater than or equal to 0, we're going to say greater than 0 for an irreversible spontaneous process. This is the second law of thermodynamics. Does anyone need a handout? Okay. Okay. So the entropy of the universe is increasing. Another way to state the second law of thermodynamics is to say that G is equal to H minus Ts. We define a new state function called the Gibbs free energy, and under constant temperature and pressure conditions, the second law of thermodynamics becomes change in Gibbs free energy, which is equal to delta H minus T delta S. Yes? We're not done yet. The second law of thermodynamics, which is written here, can be rewritten for constant temperature pressure processes as
does alpha have to be greater than 0? It has to be less than 0.
Has to be less than 0. Delta G is less than 0 for a spontaneous, irreversible process. Very, very, very important. Questions? This is the second law of thermodynamics. What is the third law of thermodynamics? Anybody remember the third law of thermodynamics?
It has to be 0.
It has to be 0. What has to be 0?
The temperature has to be 0 Kelvin. Or it can't.
One way to say the third law of thermodynamics is to say that absolute 0 is unattainable. Okay, but that's not a very useful way of saying this third law of thermodynamics for chemists. What is the better way another way of saying the third law of thermodynamics? The entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. The entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. Okay, the entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. And because of that, we can assign absolute values for entropies. You cannot assign absolute values for enthalpies. You cannot assign absolute values for Gibbs free energy. You cannot assign absolute values for internal energies. But you can assign absolute values for entropy. Okay, so here what I've done is spend 5 minutes talking about what we did last time, and this is one of the many suggestions that I got from you guys. I want to really focus in on the negatives rather than the positives. Okay, there were a lot of positive things that were said. I'm just going to mention 2 positives. Frida is super helpful. Okay, I hope at the very end of the semester we will give Frida a standing ovation. Okay, the second, the only other item I want to emphasize in terms of the positives is the pace of the lectures. I think 99% of the students felt that the pace of the lectures had improved, and that currently we're going at the right pace. So I want to look at some of the other suggestions. The answers for the the multiple choice questions, people said that I should explain why the answer is the correct answer, and I will start doing that very soon. Difficult to access movies, I think that problem has been fixed. Frida has now put them on YouTube. More problems in the lecture notes. You know, I'm ambivalent about that because I give you so many problems in terms of review problems. I give you problems for your assignments. I give you problems on your multiple choice questions. I give you problems on the quiz. I give you problems in your practice midterms. And then I give you problems on your tests. So I think, you know, there's a lot of avenues to get hold of problems. When describing molecular orbitals in a drawing, I should explicitly state where each come from. I'm a little bit confused by this statement, and I hope whoever wrote that will explain to me what you mean by that. The other suggestion was to show us how to do the problem first. More problems on the board without partners. A couple of you suggested that. Again, I'm not very keen on doing that because I think you learn so much by talking to each other. Okay, so you know, I'm going to continue to have you work together in doing problems. Post outlines earlier. Okay, my intention was to do that starting today, and of course I failed, so I photocopied copies for everybody, I think. But if I don't give you 24 hours time to print out the outlines, I will make copies for you. Okay. More bullets. You know, the lectures to be in bullet form. I'm not very keen on doing that. I think my lecture notes are very concise. If you had to read the textbook, the number of words would be at least a factor of 3 higher. So I'm going to continue the way I'm doing my lecture notes. Overwhelmed by the footnotes. A couple of you said that. And again, what I'm going to try to do is to make clear what is optional material. I'm going to make a bigger effort, but I'm going to continue to keep the footnotes. Because one of the things that really frustrates students is not knowing where things come from. At least I want to tell you, give you some idea of where things are coming from, even though the material is beyond the scope of the course. Okay? But I'm going to do a better job trying to delineate the material that is optional. Draw, write diagrams on the board. You know, that's a good idea, just that I can make mistakes in drawing. My drawings are not as clear, not as colorful, and you will make mistakes in copying the drawings. So I prefer to have these drawings, which I have gotten from so many different sources. And I think these are the best drawings that you can find for each of the concepts that I'm trying to illustrate. I feel that I am going to continue to do what I'm doing there. Quizzes should be more challenging. You know, there's one student, you know, I'm not. Sorry? I didn't hear what you said. No. Okay, make the diagrams bigger. Okay, I'm going to try doing that starting today. Issue with the textbook. I didn't quite understand what the problem with the textbook in the library is. I'm happy to give you, I have a couple of copies of the textbook, so I'm happy to give you my personal copy if you find that the textbook might be useful. And a lot of your friends have copies of this textbook. And you can buy this textbook for less than $5, which is the maximum you should ever pay for a textbook. Right? Some of you said that AP Chem was required for this course. I don't think so. The expectation is that you've had 1 year of chemistry. Somebody wanted MCQ, multiple choice questions every week. We'll have a total of about 9 multiple choice questions by the end of the semester. So it's almost every week, not quite. More visuals. I try my best. I try to show you as many movies as possible. I'll try to do more if possible. I get excited at the end of the lectures. Okay, I'll try to keep my excitement down at the end. Summary sheet at the end of the lectures. I think I have a summary sheet at the beginning of each lecture. I really think, whether it's at the beginning or at the end, it doesn't make much of a difference. So I'm not going to make a change there. Too many people at the office hours, conflicts with work, hard to come at night. So I'm going to start having office hours on Mondays from 10 to 11 in addition to the office hours that I've been having before. So, always remember that I'm happy to meet with you at any time as long as you give me advance notice and we can find a mutually convenient time. Point out connections between new material and old material. I'm trying to do that starting today. And review previous lecture, review at the end of each lecture. These are all connected. Highlight important stuff. I try to do that, I think, as much as I can. The first page of the notes really highlights the important stuff. Okay, call on someone, anyone. Okay, this is the idea that I'm still toying with. What do you think?
No.
I like it. I didn't write it either.
I'm sorry?
I like it, but I didn't write it.
Okay, you didn't write that. Okay, I hope. All right, I'm still thinking that there is a lot of material that has been published about the benefits of cold calling. So I still haven't decided on that. Some important information in the footnotes, yes. The reason I put some of the important information in the footnotes is that they are supposed to clarify a statement that I have in the main text. For me, logic is so very important that I don't want to put that information in the main text because that will make the logic not progress correctly. So that's why I put sometimes important information from a previous lecture in the footnote. But I'm going to really try hard to make clear what is optional material and what is material that you need to understand. All right? So thank you very much for the time you took to answer these questions. It took me a long time to scan those because a lot of the material was written in pencil, so I had to photocopy, make it darker, and then scan it, and then put it all together. But thank you very much for your time. All right, so let's go back to the lecture for today. One of my favorite websites. Whatever you do, you've got to make sure to keep your molecules happy. No. Why is this not? This is a. Why can't I? I just put the Word document. Oh no. What does that mean? What should I do? All right, I'm going to let you guys do this at your leisure. I think it's a very interesting website which demonstrates to you that if you have a finite number of molecules in a system, for short periods of time, it is possible to violate the second law of thermodynamics. Because the second law of thermodynamics is based on probability. Okay? So the guy took the book and threw it up into the air, and the 536 pages, showed up on the ground totally in disarray. But there is still a very, 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 very small possibility that those pages could fall in the correct order. Okay? So the second law of thermodynamics is based on probability. And when you have a small number of molecules, you can violate the second law of thermodynamics. So I hope you will look at this website at your convenience later on. All right, so this is what I just talked about now. If delta G of the system is less than 0, the system is spontaneous in the forward direction. If delta G of the system is equal to 0, the reaction is at equilibrium. If delta G system is greater than 0, the reaction is spontaneous in the opposite direction. All right? So, remember that delta G is equal to delta H minus T delta S. So there are two contributions, delta H and delta S, that determine the value of delta G. Okay, and you can have four possibilities. If delta H is negative and delta S is positive, at every temperature, delta G is going to be negative, and therefore the reaction is going to be spontaneous at all temperatures. Okay, so if you have delta H is positive and delta S is negative, then delta G is going to be always positive, and the reaction is not going to be spontaneous at any temperature. Okay? So cases 2 and 3 are interesting. Case 2 is called an enthalpy-driven process because case 2 has a negative delta H. That means that process is made favorable because of the enthalpy being negative. The delta S being negative makes the process unfavorable. So if the reaction is spontaneous, it is spontaneous because of delta H minus being negative. And that is called an enthalpy-driven process. So let's look at a movie.
When cooled, gaseous NO2 forms gaseous N2O4. The entropy of the system has declined because two molecules have been converted to one. We say this reaction is enthalpy-driven.
So this reaction is spontaneous, which means that delta G is negative, but delta S is negative also. So this reaction is spontaneous only at low temperatures. So NO2 going to N2O4 is a spontaneous reaction only at low temperatures. Because at higher temperatures, then the delta S term is going to overwhelm the delta H term, and delta G is going to become positive, and the reaction is not going to be spontaneous. So in this reaction, is heat a product or a reactant? Yes, Angela. So you want to put heat as a reactant here rather than heat as a product here. What do other people think?
Would it be the other way? Because when you're putting in enthalpy, you're causing the temperature to go up? Or you're putting in heat, so this heat is going to be part of the products?
So look at this. We're looking at the case where delta H is minus and delta S is also minus. If delta H is minus, is that an exothermic or an endothermic reaction? Exothermic. So heat is being produced, or is it being absorbed? Produced. So heat is going to be a product. Okay? All right, so what we are interested in doing is figuring out what delta G of the reaction is. This is what we are interested in finding out. Because if we find out this, and if we find out that it is less than 0, that means that reaction is spontaneous. That's a favorable chemical reaction. You can do that in a lab, you can do that in a factory and produce what you're trying to produce. So this is a very important question. What is delta G reaction? And the rest of the lecture today is about how do we calculate delta G reaction. Okay, one way would be to tabulate the value of delta G reaction for every temperature and every pressure that you can think of for every chemical reaction. That would take up every book in the universe. So what we're going to do instead is to define a value called delta G reaction with a superscript O or 0, and we're going to say that that is the change in the Gibbs free energy when reactants in their standard state are converted to products in their standard state. So we want delta G reaction, but we're going to try to calculate that by calculating delta G reaction 0 first. If we know the change in the Gibbs free energy when reactants in their standard state go to products in their standard state, then we can use this value here and get this quantity here. And we're going to find a relationship between these two. So right now, what we're interested in doing is figuring out this value here. How do we get delta G naught reaction? What is the change in the Gibbs free energy when reactants in their standard state go to products in their standard state? What are the standard states? And for a gas, we assume that we have an ideal gas at 1 bar. What is 1 bar?
1 atmosphere.
It's approximately 1 atmosphere. It's to within 1%. To be more precise, it's 100,000 pascals. For a liquid, the standard state is a pure liquid at 1 bar. For a solid, it's a pure solid at 1 bar. And for a solution, it's a 1 molar concentration. So we want delta G reaction, but we're going to get that from delta G naught reaction. But how are we going to get delta G naught reaction? We're going to get that from the Gibbs free energy of formation of the reactants and products in their standard state. Okay, so what is the standard free energy of formation of a substance? It is defined as the change associated with producing 1 mole of that compound from its constituent elements in their most stable form under standard state conditions. So what is the Gibbs free energy of formation of N2 gas? 0. Okay? And one way to get the Gibbs free energy of formation for any substance is to use this equation here. Where did this equation come from?
That's the same one as the Gibbs free energy for the reaction. And then we just change them all to energy of formation. So we just added.
Yeah, this comes from the definition of Gibbs free energy. The definition of Gibbs free energy is G is equal to H minus TS. So we're going to say that we get the Gibbs free energy of formation from the enthalpies of formation and the entropies of formation. So the standard free energy of formation of all elements in their most stable state is 0. So here are the Gibbs free energies of formation of several substances. Okay? Here is a question that asks you to use these values here. There are 2 tables here. Use these 2 tables and calculate the Gibbs free energy of formation and compare it to the table over here, which gives you the Gibbs free energy of formation. So these 2 tables at the bottom give you the Gibbs free energy of formation, enthalpies of formation and entropies of formation. I want you to combine these 2 tables and calculate the value of the Gibbs free energy of formation of ozone and compare it to the table that's on the top. So can you take a couple of minutes? Actually, can you work with a neighbor, because this is not a trivial question. It requires some amount of manipulation, so please work with your neighbor and see if you can work this out.
So we know that the temperature is in between change and I think the change in age is going to be this way.